Welcome back, viewers, to another new topic on HEE online series. So, in this lesson, we are going to be talking about Kirchoff's current law, or simply KCL. So, and this can also be referred to parallel law. So, because this topic helps us to deal with problems under parallel circuits. So, let's get down to the business without wasting much of our time. So now we are going to approach KCL, Kirchhoff's current law, in two ways. So the first way we are talking about here is what we know as um, Kirchhoff's current law uh, 1, which is KCL I. So this law states that the algebraic sum of the total current entering and exiting a node or junction of the circuit is equal to 0. So which means the algebraic sum of the current I in any circuit, parallel circuit, is equal to um, 0. So this is simply what this first law is talking about. So that is what the first law is talking about. So how can we analyze this? Let's quickly take a look at this shape that I'm going to draw here now. So here is what we have. So if you look at this now, it contains two things, which are nodes and as well as what branches. That is what we have here. So, and I believe we can ascertain the number of nodes we have here. So those that have been following us, we know that what we have is just a single node, which is the one that is present here. So which is the one that is holding all these branches together. So these are branches. We have like 6 branches here, and we have just one node. So that's what we have in this diagram. So if we are going to analyze this diagram based on the first law of under first method under the Kirchhoff's current law, so we are going to uh, write it in form of this way. So we say um, by applying KCL, so under the first law, so we are going to have um, um, so according to what we have in this diagram, we can see these arrows are pointing towards the node. We can see all these arrows on I1, I2, I3 are pointing towards, while the arrows on the I4, 5, and 6 are pointing outwards. So which means these are the um, current that are entering the node or the junction, while these ones are the current that are leaving or exiting the node or junction. So we are going to put it this way. So which is I1 plus I2 plus I3 minus I4 minus I5 minus I6 equals 0. So according to the first method of the Kirchhoff's current law. So why do we assign positive here? Because the arrows, they are the one entering the node, while these ones are the one leaving. So we represent this one with negatives. So no matter what is going to be, Kirchhoff's law is said to be obeyed when the sum of the arrows current that are entering a node or junction is and the ones that are leaving or exiting the junction are equal to 0. So that is the first steps we are going to take note. So under this now, we are going to write some properties that we need to take note under this first method. So let me just put it down here. So here is it. So from what we put here, so we analyzed here. So this is the secret behind it. So which means whenever you have uh, a current in KCL, so a current in KCL that is entering the node, you should assign what we know as a positive sign. So, and whenever we have a current that is exiting or leaving the node, we shall assign a negative sign. So you should take note of these two secret or trick to it. So, which means assign a positive sign for current in KCL if I is entering the node. Assign a negative sign for current in KCL if I is exiting the node. We should take note of these two. So now, without wasting much of our time, let's move to the second part of the KCL using the second method. So, without wasting much of our time, this is the second part of the KCL, which we can regard as the second method. It states that the total current flowing into a node or junction is equal to the total current flowing out of the node. So this is a little bit the same with what we have here, so we can use this method. So if you are going to analyze what we state here in this second method with this symbol, so we are just going to manipulate this a little bit, so which means all the current that are entering, which is I1, I2, I3, is going to be on a side, and the one that are leaving is going to be on the other side. So which by the time it is solved in a circuit and a real circuit, so it should give the same result as well. So not just a law, but it's a law that is applicable in circuit analysis. So now, so what we meant now is like, so it's going to be like uh, the sum of current, the algebraic sum of current, you can call it I in, that enters a node must be equal to the algebraic of current. We can term this one I out, that leaves the uh, that leaves the node. So that is what it means. So from here now we can say by excuse me, from here now what we can see here, by applying KCL, the second version of it, we can say I1 plus I2 plus I3 equals I4 plus I5 plus I6. So that is all about the second method of KCL, which means the total sum of current entering a node is equal to the one that are leaving or exiting the node. So now let's go straight to the application and verification of KCL. But before we go to the verification of KCL and some application, let's quickly see how this second law, let's see how it works. So there are some secrets behind it, the application of your science and wherever you see them. So let's quickly analyze that. So here it is as simple as this. So we have assign a positive sign for I in if current is entering the node. Assign a negative sign for the same high in if current is exiting the node. So it depends on the way you want to approach it. So it depends on you in this case. So on the other hand, assign positive sign for I out if current is exiting the node. Assign negative sign for I out if current is entering the node. Positive for I out and it's negative for I out. So you can see it is happening in the opposite side. So it depends on the one you want to use. It is happening in the opposite side. So which means if you want um your I in to be positive, definitely your I out will be negative. On the other hand, if you want your I out to be positive, definitely your I in will also be negative. So in this case, we applied a positive for our what do you call it, our high in, and our high out is going to be negative on the other side. So by the time we are transferring it, it will be equal to each other no matter what. So even though they are on the same side, they are going to be equal to each other. So that is what we apply in our own case here. So whichever the sign you choose to apply, you are still going to arrive at the same result. So that is the secret of what they call it, of the second method of Kirchhoff's current law. So um, we can also compare this to a particular water that flows in a pipe. So it doesn't matter whether the pipe is wider at one end and tiny and narrow at the other end. So which means, let's say for example we have a pipe that is in this form. Excuse me, don't mind my, I'm not really perfect at drawing that, like that. So let's say we have something like this. This is a narrow pipe. This pipe is wider at this end, and on the other end is very, very narrow. So let's say we have something like this, which we can use to represent the middle. So so this is what we have here. So no matter what, so let's say we have water coming from different channel on this on from this side B, C, D. Let's say water is coming from different channel, and this is just a single opening here. So it doesn't matter. We are going to have the same amount of water that's entering here is the same amount of water that is going to come out here. It's just a matter of time. So that is the secret behind the Kirchhoff's current law, which is the second method. So now let's take some examples that can give us a better understanding of the verification of Kirchhoff's current law. So here is what we have. So from this question, we are to determine current in I O. Oops. So I think it should be I4. That is what we are. That is the unknown we have here. I4. So determine the current I4. So if I4 is the unknown uh, in this um, current, you can see. Let's follow the direction. We can see I1 is entering, I4 is entering, even though we don't know the value. I2 is out. I5 is also entering. So um, let's say we can apply any of the Kirchhoff's current law. So I think we have done two. So let's make use of the first one. So the first one say applying KCL, which happens to the first one. So which goes to that is algebraic sum of current that enters and that the algebraic sum of current that enter and leave or exit a junction is equal to 0. So that is what we are making use of. So now um, we are going to use, let's quickly recall the rules or the secret we gave us earlier. So we said we should apply positive sign for current that is entering in the node, and the one that we should assign negative sign for the current that is exiting the node. So I think that is what we are going to use as far as the first method is concerned. So that is what exactly we are going to do. So if we look at I1 is entering, so we are going to have positive I1. So which other one is entering? Okay, let's go that way. So is there another one that's entering? So I3 is entering, positive I3. So so we have which other one? We have I4 is entering. We have positive I4. So it's only I2 that is leaving. So it's going to be, sorry, positive I4. So it's only I2 that is leaving. So we are going to have negative I uh, I2. So that is the one that is leaving. So the sum of everything is going to be 0. So of course we know that we are going to put negative here. Okay, because if you are going to have an additional sign, plus times minus is still going to give you a negative sign. So by the time you can substitute your value straight from this place now. So we have been given our current I1 to be what? To be 10, plus our current I3 to be 5 ampere. 5 ampere. Current I4 is what we are looking for, unknown yet. So the next thing, minus current I2, which is 20 ampere. Everything equals to 0. So the next thing we are going to be doing now, we are going to um, collect the like terms, or we should have this thing first. If you permit me, I will do that. So if you add this one to this one, it's going to be 15, and 15 minus 20, so it's going to be minus 5. So we are having I for minus 5 ampere, which is equal to 0. By the time we transfer this one to the other side, we are going to have I4 equals to 5 ampere. So that's the value of our I4 in this question. I noticed two things which I can also term the property of the physical property of KCL. The first thing I noticed that charges cannot accumulate in a node. So which means what arrives at a node is what leaves that node. So and this can also result from conservation of charges. So that is, charges can neither be created nor destroyed, or the amount of charges that enter the node equals the amount of charges that exit the node. So another things we can notice is that we can notice the continuity of current at every point in a circuit. So what do we mean by this? So we mean that charges cannot stop at a point. So which can also compare to the flowing of water in a pipe, or current in a conductor, which confirm the continuity of current in a conductor, which means current or charges is what it's continuous. The process or the movement of current or charges in a circuit or conductor is always continuous. So that is what we can gather. So before we quickly move away from that, let's look at some method or procedure to solve complicated problems under KCL. So though we are not going to apply that in this topic in this lesson, but we are going to apply it in our subsequent lesson, or next lesson rather. And we said in case you come across complicated problems in KCL, so the procedure here below are the necessary procedure that you should know, that you should um, take note of them, so that you can apply for easy solutions to the problems. So it does not matter which field of science the problems belong to, or how complicated they are. So the procedure for analyzing and solving the KCL is always the same. So the first thing you have to notice that you start from the unknown value in this problem and find the right equation, which is the one we got from the first method and the second method we talked about earlier, that can solve this unknown. So the second step is what determine the new unknown of the equation in the step one, and find the equation to solve this unknown. So continuous like that. Repeat the steps 1 and 2 until there are no more unknowns in the equation. And the last part is substitute the solution from the last step into the previous equation, just like what we did the other time, and solve the unknown. So repeat until unknown in the original problem is finally solved. So I think that is where we are going to draw the curtain on today's lesson. So please do like and send comments. You are free to share and subscribe to our channel, so that you can enjoy much videos from us. So we really appreciate you for watching and staying with us on this series. So till the next lesson, thank you very much. Bye bye.